The topic of this lecture is I/O devices. I/O devices refers to the device such as SSD or hard disk drive or network interface card, or there's mouse, of course there's keyboard. All these are peripherals. And I/O is critical to the computer system to interact with the system. In this lecture, you're going to cover how should I/O be integrated into the systems, what are the general mechanisms, and how can we make them efficiently. This is the typical layout of the entire computer system. There's CPU and there is memory. And CPU and memory is connected via the bus called memory bus. And these are proprietary usually, and this is defined by the CPU manufacturer. And then there is graphics card, and this is general I/O bus, something like PCI. And usually the faster device like graphics card is attached to PCI. This is PCI bus. And then there comes a peripheral bus. This contains SCSI or SATA. This is SATA. And there's USB. So as it gets farther from CPU, it gets slower. These days, some of the SSDs, such as NVMe-based SSD, is attached to the PCI bus because they get faster. There's two important notions. There's bus. It's a data path that is provided to enable information between CPU, RAM, and I/O devices. And I/O bus is a data path that connects a CPU to the I/O device. And I/O bus is connected to I/O device via three important hardware components. First one is I/O ports, and second one is interface, and the third one is device controllers. So we're going to deal with each of these later. Okay, this is I/O device. It contains hardware interface and internals. It consists of interface and internals. So canonical devices has two important components. First one is the interface. It allows the system software to control its operation. And internal is implementation specific. So usually this interface is standardized. So it says like a SATA or PCIe or stuff like that. And then inside SSD there is, for example, there is microcontroller, and there is some type of memory, and there are some chips. Okay, so these are the hardware interface of the hardware device, canonical device. First one is status register, and command register, and data register. There are three sets of registers. And in status register, it shows the current status of the device. For example, it's busy, or error, or idle, such and such. And command register, it tells the device to perform a certain task. It's a read or write. In data register, it passes the data to the device, or it is used to get the data from the device. By reading and writing the above three registers, the operating system can control the device behavior. So this is typical interaction between the host and the device. This is the code. When a host wants to ask the device to do something, it waits for it to be idle. So it has to wait until it becomes idle, and then it writes the data to the data register, and then it writes the command to the command register, and then if it writes the command to the command register, then it automatically starts the device and executes the command. And then the caller or the host program waits until the device is done with your request. The interesting part of this code is that the device, the host is waiting in the busy loop. So it keeps checking the state, whether it is busy or not. So this is to be shown later. It is called polling. So it keeps check whether the device is busy or not, waiting for the device to finish its request. Okay, so this is the first word, polling. In polling, operating system waits until the device is ready by repeatedly reading the status register. The polling is simple and it works, but it wastes lots of CPU time just waiting for the device, doing nothing. So it is possible it might be better to switch to another thread and execute that thread while the IO device is doing its own work. For example, there is CPU, there is a disk, and this is the thread number. So from here to here, thread 1 is being executed. And then the host asks the device to do something, and then disk is servicing the request. While the disk is servicing the request, the CPU keeps checking the disk whether the state is ready, the disk is ready or not. Once it's ready, then the CPU starts to execute the thread 1 again. Here, the problem of this approach is while waiting for the IO device to complete his request, the CPU is doing nothing. So, the engineers has proposed a new mechanism called interrupts. Right after issuing the command to the IO device, the operating system puts the caller to sleep and switches the context to another. Okay, so right after issuing the request to the disk, here the CPU switches the context to another thread and executes the next thread. When the device finishes, it wakes up the process waiting for the IO by interrupt. So the positive aspect of this approach is the CPU utilization gets better because while the disk is servicing the request from thread 1, the CPU can execute another thread. So the CPU cycle can be utilized in more efficient manner. However, interrupt is not always the best solution. This is because the context switch is not free. If the device is very quick, then interrupt may slow down the system because context switch costs the time to save the register, time to restore the register, and time to warm up the cache. So device is fast. The poll may be better option. And let me explain a different aspect of I/O. CPU waits a lot of time to copy the large chunks of data from memory to the device. For example, here the thread 1 is executing, And then before starting an I/O, it has to copy the data blocks to the disk. And then while the disk performs the requested I/O, the control is transferred to another thread and executes. The operating system executes a new thread. So this time period is being wasted by performing a memory copy. To avoid the overhead of copying the memory for CPU, they introduced a notion of DMA, direct memory access. They have developed a small microcontroller called DMA controller, and it is embedded processor. It can copy the data from one memory location to another. So to avoid the expensive and valuable CPU cycles time being used for just simple mundane process of copying the data blocks from memory to another, they use DMA. So to copy memory, they ask DMA controller to perform a copy operation from memory to another, and then performs context switch. Then right after asking the DMA controller to perform memory copy, the CPU can start executing another thread. When completed, DMA raises an interrupt and I/O begins on the disk. So how can the OS communicate with the device? So there are two approaches. First one is I/O instructions. So they provide some operating system defines separate operations like in and out to read and write from the disk or device, or they perform memory mapped I/O. So memory mapped I/O means that there is registers like control register, status register, and device data registers, but they are available as memory locations, something like load store instructions. So the operating system load or store to the device instead of main memory. Let's look at the actual code. You're going to review the details of the IDE device driver. There are 4 registers: control register and command block registers, and there's status register and error register. So this is details. So this is control register. It is 8-bit, and its address is 3F6. This is the address of 3F6. So apparently in x86 operating system, they perform memory mapped I/O. And it consists of 8-bit, 0000, and the first bit of the least 4 bits is 1, and then the next 2 bits represent whether the interrupt is enabled or not, and the value is reset or not. So if E is 0, then it means that interrupt is enabled. And there is command block registers. Through the command block registers, host and device communicates the data. So host writes the data blocks to the command block registers, or the host reads the command block register to retrieve the data read from the device. So there are roughly 8 distinct port. So there are data port and header, and there's sector count and LBA, and then so there's LBA, and then there is command and status, 1 byte. Okay. So for LBA, we are allocating, this is 24, and there is another 4, so 28 bits, and 4 bit for the drive ID. And status register consists of 8 bit, and the status register, each bit of the state register has different values. So first bit, bit 7 is busy and ready, fault, seek, and stuff like that. and this is error register. So let us explain the basic protocol of IDE driver, IDE device driver. The basic approach is first, it wait for the drive to be ready. When the drive is ready, it write parameters to the command register. It write parameters to command register. It writes sector count and address of the sector and drive number. And it issues, it sets the command to the command register. This is read or write. So for write, we have to transfer the data first. And then it handles interrupt, and then it handles error. This is code for the driver. First, it acquires the lock. Second, it walks through the linked list of the request till the end. And at the end, very end, it appends the block that needs to be read or read to. If the queue was empty and if the just requested IO is the only request, and it starts the request immediately via calling IDE start, IDE start request. We're going to deal with the details of the code later. And until the request is served and request is complete, it has to be put on the sleep mode. So it checks if the flag is ready, it goes into sleep mode, and then before it goes into sleep mode, it releases the lock. And after getting out of the loop, it releases the lock. So that's how it works. Okay, so let's go into the details of the IDE start and request that has been called inside the IDE read-write. First, wait till the IO device is ready. And if the IO device is ready, then it enables the interrupt. And it sets the sector count. And then it sets the LBA. And then if the flag is dirty, okay, if the flag is dirty, it means that the current request is right. And then it says the command to the right. And then it transfers the data. It writes the data blocks to the data register. And the amount of data blocks to be written is 512 divided by 4, which is 128. If it's not right, then sets the command as read. So this is how we start the request. Let's get into details. The first, the IDE start request. The first line of request is wait for the device to be ready. So inside the function IDE wait ready, it checks. It keeps reading the register until it is ready. And so it reads the status register and save it to R and check if the device is busy and check if the device is ready. So if the device is not busy and is ready, it get out of the while loop. So this is how the IDE wait ready works. And then next step is to enable the interrupt and the sector count. So it enables the interrupt. And then it sets a sector count. This is how we specified LBA. This is how we set the data transfer for the write command. If the dirty bit is set, it means that it is a write command. So we set the command as IDE write, and then we designate the data blocks how many bytes we need to write to the data register. So amount of data to write is 128 byte. And the out SL is the macro. The first parameter is the address, and then second one is the address of data, and this is number of bytes we need to write. Lastly, the last command is read. If it's read command, which means that the block is not dirty, then it sets the command as read, and it sets the command register as read. This is interrupt handler for a given IO. If the request was read, it is read if you look at the dirty, and if it's dirty, it's clean, then it's read. Then it reads the data register, and the amount of data to read is 128 byte. And then after reading the data block, it sets the valid bit and dirty bit and wake up the caller. And if there is another request to serve, then it starts to service the next request via calling ID _ start _ request. So this is how we handle the IDE interrupt. How does the operating system interact with different types of interfaces? The solution is abstraction. So via providing the layer of abstraction, the operating system can interact with any type of interface. So in summary, to save the CPU cycles for an IO, we use interrupt and we use DMA. And there are two ways to access the device register. First one is memory mapped IO and explicit IO instruction. And we have covered the details of the device driver code.